In the last video, we tried to look at radioactivity and basically the formulas also. So we said radioactivity is the spontaneous disintegration of an unstable nuclei. Accompanied by the release of alpha particles, beta particles, and gamma particles, and also with the release of what? Energy. So you have an atom with an unstable nuclei. So since it is unstable, so it splits into two or more daughter cell. Sorry, I'm actually referring this to biology, but this is chemistry. Sorry, physics. So it splits into two daughter nuclides, alright, and also releases energy. So we said that this splitting is irrespective of the chemical property of this atom and also the physical property, and also the disintegration is independent of external factors such as pressure. So the disintegration doesn't depend on the pressure, temperature, right? So it doesn't depend on any external factor, so it occurs on its own spontaneously. Right? So, and we also looked at the graph. You see, so we plotted the graph of the amount of radioactive material against time. Right, so we say time in seconds, and this axis for the number of or the amount of particles or the amount of radioactive material, n, right? N. Okay, so we said the graph looks somewhat like this. You see, so this graph is actually called an exponential decay graph. Exponential decay graph. You see, so it looks more or less in the form of, from the mathematical point of view, it looks more of like y equal to e to the negative x. All right. So of course we are not looking at mathematics, so let's just look at the physics aspect of view. All right. So we said if you plotted time in this axis and the amount of radioactive material in this axis, that if you started with some amounts, n1 at time equal to t1, right? And it took another time t2 for this thing to decay to the half of the initial n over 2, and also it also took some time. I might not draw this to scale, but I hope it makes sense. Okay, so this is n, so this will also be the half of this, so it decays into the half of this. We have n over 4, so half of n 1 over 2 is n 1 over 4. So we said that t2 minus t1 or t3 minus t2 is actually the half-life of the radioactive material, and we also express the uniqueness of this half-life, that every unstable nuclei that wants to undergo disintegration has its unique half-life. And in the next video, we are also going to look at constant, the decay constant, which we're not going to do in this video. So basically, in this video, we're just going to be solving examples using the formula that I provided initially. Okay, so let's look at the first example. So in this example, in 24 days, a radioactive isotope decreases in mass from 64 grams to 2 grams. What is the half-life of the isotope? So let's look at the solution. Let me change color. All right. So we, from the formula that I gave, the half-life is equal to the time t over logarithm base 2 of r, and also this is also equal to t over the number of half-lives, right? So we asked to find the half-life. So t is 24. So in 24 days, so we have 24 days logarithm base 2 of r. What is r? We said r is n1 over n2, right? n1 over n2. And what is n1 in this question? The n1 is the initial. So the initial is actually 64. So we have 64, which is n1 over n2. What is n2? n2 is 2, right? So we have 24 over logarithm base 2, right? So this is 64 divided by 2 is actually 32, right? So we have the half-life is equal to 24 over logarithm base 2. Well, I'm having problem with my writing materials. Okay, let me shift that up a bit. Logarithm base 2 of 32. Now 32 is actually 2 to the 5th power, right? And we know that by the logarithmic law, we can take this 5, flip it down here, right? So that we have 24 over 5 log 2 of 2 now. So there's no 5 here again, so we flip the 5 down. Now logarithm of 2 base 2 is actually 1, so we now have 24 over 5 times 1. 5 times 1 is still 5. So we now have 24 divided by 5, which is actually 4.8. So we have 4.8 days as the half-life. All right. So let's check the example 2. So before I do this, try this out. Okay. So we have the half-life of a radioactive material is 6 hours. Right. So solution. So the half-life, in this case, we're given half-life T capital T to be 6 hours. So what is the quantity of 1 kilogram of the material? Sorry, what quantity of 1 kilogram of the material will decay in 24 hours? Now, what is 1 kilogram here? After that is the initial, right? N1, 1 kilogram. So what quantity of this will decay in 24 hours? What is 24 hours there? That is T, small t, 24 hours, right? Okay. Right. So let's look at, of course, now they said what quantity would decay. Now, quantity we said quantity that we decay from our formula in the last video. If you've not watched that, go check that out. So we said the quantity that we decayed, which is Nd, is N1 minus N2, right? Okay. Now let's see. Let's leave this aside first. First, let's try to see the number of half-lives here, because we know that T is equal to capital T over number of half-life. So we now have T, capital T is 6 and small t is 24 over number of half-lives. That means number of half-life would be 24 over 6, which is 4, right? And note, from those formulas we said R is equal to 2 to the nth power, right? So what is R in this case? R will be 2 to the 4th power, which is 16, right? 16, right? Yeah. Okay, so we said R is actually n1 over n2, which is actually 16, right? Okay, so let's see what n1 is. So let's see what n2 is rather. So let's divide, let's put a line to differentiate that. So we have n2 is equal to n1 over 16 over 16. All right, n1 over 16. I'm running out of space, so let me clean up some space here. Yeah, let me clean up the space. Okay, so we now have n2 equal to n1 over 16. Now we said nd, which is the number that decayed, or the quantity that decayed at that given amount of time, which is 24 hours, is n1 minus n2. Now what is n1? N1 is actually 1 kilogram. 1 kilogram, right? So we have minus, what is n2? N2, we just said n2 is equal to n1 over 16, right? N1 over 16. And what is n1? N1 is actually 1. So we have that to be 1. So of course we just have 1 minus 1 over 16. So to make things look more nicer, we know that 1 is same thing as saying 16 over 16, right? So we now have the same base. So we have 16, then 16 minus 1 will be 15. So we have 15 kilogram. All right, so let's check out the next example. As usual, you pause the video and try this out. So we have a radioactive sample initially contains n atoms. After 3 half-lives, the number of atoms that have disintegrated is. Now a radioactive sample initially contains what? N as the initial number of atoms. So n1, our n1 in this case is actually, let me change color, because I this color is actually boring. Let me use black. So n1, which is the initial number of atom, is actually n in this case, right? N. So we have n. So after 3 half-lives, we have 3 half-lives. After 3 half-lives, the number of atoms that have disintegrated is, so number of atoms that have disintegrated. Now number of atoms that have disintegrated will be number of atoms that have decayed, right? Nd, right? And we see that this is actually equal to n1 minus n2, right? So note we said that R is equal to 2 to the nth power, right? So we have 2 to the 3 power because n is equal to 3. So this is actually 8, right? So R is equal to 8. Okay, and this is equal to n1 over n2, right? n1 over n2. So let's see what n2 is. n2 will be n1 over 8. So let's now calculate the the number of atoms that have disintegrated, Nd. So that will be N1 minus N2. What is N1? N1 is actually N minus N2. What is N2? N2 is actually N1. N1. What is N1? N1 is actually just N, right? Over 18. Okay. And this will be, of course, we could make this simple because we need to have the same base in order to make things simple. So if we put in 8 here, we put in 8 here too at the top. So we have 8 over 8 is actually 1. So we just have 1 multiplied by n, which is still the same thing. So we now have same base, which is 8. Then 8n minus n, that will be 7n. Right? So option D is correct. Okay, so let's check out the next. Okay, so example 4. So check this out and try this out first. After 3 half-lives, the fraction of a radioactive material that has decayed is, okay, after 3 half-lives, so solution. So after 3 half-lives, so n is 3, right? After 3 half-lives, the fraction of radioactive material that have decayed is, so fraction that decayed, of course, from the formula given in the last video, we said fraction that decayed is actually equal to what? Now, number that decayed over the initial amount, right? Okay. All right. So first, since we know that R is equal to, which is the disintegration ratio, is equal to 2 to the nth power. So we have 2 to the third power since n is equal to 3, which is 8, right? And this is going to equal to, because R itself is equal to N1, because R itself is equal to N1 over N2, right? Okay, so let's see what N2 is. N2 is equal to N1 over 8, right? From this formula. Okay, so what is FD now? Which is fraction that decayed. So FD will be ND. What is ND? ND is actually N1 minus N2. That will be all over N1, right? Okay, so we now have, what is N1? Of course, N1 is actually N1, right? N1 is actually N1 minus N2. What is N2? N2 is equal to N1 over 8. N1 over 8. Then everything over 1. Right? So let me clean up some space. Okay. So FD will be, of course, since n is common, so we could factor it out. So we now have N1 into bracket 1 minus 1 over 8 over 1. Right? Also, we can, over N1, rather, N1. Okay, so all we did here is just, since we have N1 here and N1 here, we factor it out. So we have N1 here, we factor it out. So we still have our N1 at the denominator. So it cancels out with this. So we just have 1 minus 1 over 8 over 1. Right? Which is still the same thing as this 1 minus 1 over 8. Now, 1 is actually 8 over 8, right? Because we always want to have the same base, so that it will be easy for us to do the calculation by heart. So we have 8 as our common denominator. So we have 8 minus 1 now, we have 7. So 7 over 8 is the answer. So option D is also correct. Okay, so this is example 5. So the half-life of a radioactive element is 24 hours. So capital T is 24 hours. And be sure to try this out first. Okay, so calculate the fraction of the original element that would have disintegrated in 96 hours. So this is to calculate the fraction of the original element that would have disintegrated. So fraction that would have disintegrated also means fraction that decayed, right? Okay, fraction that decayed, right? Fraction that decayed. Okay, and that is actually ND over N1. Now what is this 96 hours here? Of course there is small t, 96 hours. All right, so first let's see. Of course R is equal to 2 to the n's power, right? So what is n? We don't know what n is, so let's find n, which is the number of half-lives, since t is equal to big T is equal to small t over n. So big T is actually 24, small t is 96, then over n. So n is equal to 96 over 24. Let me press the calculator for that. 96 over 24, and there is actually 4. So n is 4, right? N is 4. So we have R is equal to 2 to the nth power, which is now 3, right? Sorry, 4 rather. And this is 16, right? This is 16, and we always know that R is equal to N1 over N2, right? So let's find out what N2 is. N2 is equal to N1 over 16, right? N1 over 16. Okay, so let's erase some space. Now our goal is to find the fraction that disintegrated, or the fraction that decayed, right? The fraction that decayed. So fraction that decayed will be, of course, is ND over N1. What is ND? N1 minus N2, right? Okay, and FD will be N1. What is N1? Of course, we don't know, but we actually care about the fractions, right? Fraction. Okay, so N1, so we still leave it like that. N1 minus, what is N2? N2 is actually N1 over 16. N1 over 16. And everything over what? N1. Then as usual, we factor out N1 because N1 is common between these two terms. So if we should factor out the N1, of course, this N1 cancels out this. So we just have, well, let's depict that. Let's see how that happens. Let's not just cancel like that. So we have N1 common between both of them. So we have 1 minus, we now have 1 over 16 left here, 1 over 16 left here, then everything over N1. So this cancels out with this. So we now have 1 minus 1 over 16 over 1, which is still the same thing as 1 minus 1 over 16. Right? Of course, we always want to have the same base, right? So we make this 16 over 16. So FD will be 16 minus 1, that is 15. So a fraction that would have decayed will be 15 over 16, right? So this is correct. So this is example 6. So be sure to try this first. Okay, so we have a radioactive isotope has half-life of 8 days. Half-life 8 days. 8 days. What fraction of the atom will remain after 72 days? What fraction will remain, right, after 72 days? 72 days there will be small t, right? Of course, from the last video, we knew that fr is actually n2 over n1, right? Okay. And also, we also said that n2 over n1 or fr is actually 1 over r, right? Which is the disintegration ratio. Okay. So first, let's find the disintegration ratio. Of course, we know that the disintegration ratio is actually 2 to the nth power, right? So using the formula t equal to t over n, let's find n. So n is equal to t over t, small t over big T. So what is small t? Small t is actually 72 over 8. So we have 72 over 8, and that's actually 9, right? So we have 9. So what is r now? R is actually 2 to the 9th power, right? 2 to the 9th power. Okay, and that's actually 512. So fr in this case will be 1 over r. What is r? 512. And if you should press the calculator, you see that you have 1.953 times 10 to the negative 3, right? So this is the fraction that will remain after 72 days. Okay, so example 7. So we have a radioactive substance has a half-life of 20 hours. Capital T, 20 hours. What fraction of the original nuclide will remain? Fr, always, this is always this, or n, n2 over n1. Okay, so what fraction of the original nuclei will remain after 80 hours? So small t is 80 hours. So let's find what the number of half-lives is. Of course, number of half-life is going to equal to small t over big T, right? Okay, so small t is actually 80 hours, big T is actually 20 hours, and this is actually 4, right? So what is r? R is actually 2 to the nth power, right? And what is n in this case? 4, right? So we have 16, right? So we have 16. In this case, fr, which is fraction that will remain after 80 hours, will be 1 over r. What is r? 16. Okay. So example 8. So we have two radioactive elements now in this case. So we have two radioactive elements, A and B, and each have half-lives 100 and 500 years respectively. So 100 and 500 years respectively. So the half-life of A is 100 years, and that of B is also 100 years. 550 years, right? So sample A and sample B are sample A and sample B initially contain equal number of atoms. So at some particular time, n initial of A is equal to n initial of B, right? So they have initial number of atoms. So what is the ratio of the remaining atom? Ratio of the remaining atom, which is n2 of A, of the remaining atom of A to that of B. So ratio of N2 of A to that of N2 of B. So let's figure what this is. First, let's see if there is a way we can make this simple. Okay. It looks as if we have run out of space here. Okay, there's a space over here. So let's take some parameters from here. So we have TA is 100 years, TB is 500 years. Of course, TB is not tuberculosis, just T sub B, right? Okay. So let's see. First, let's look at our formula. T equal to capital T, T, which is the capital T over small t, big T equal to small t over number of half-lives, right? So let's see. Now, since they have equal initial amounts of this, so first let's find the half-life for each, right? Half-life, number of half-lives for each, right? So since we know that TA is equal to 100 years, right? 100 years. Sorry. And actually, we are actually considering the ratio of the initial amount of A to that of B after time 200 years. So small t is 200 years. So we have small t to be 200 years. Of course, number of half-life will be, as number of half-life for A will be small t over big T A. So we have 200 over 100, which is what? 2, right? So R for A is actually 2 to the nth power, right? Of course, which is 2. 2, which is 2 here, because what n is what? 2 in this case. So we have 4, right? So we have 4 in this case. Now, since we know that TB is 50 years, right? That means NB will be small t over TB, which is 200 over 50, which is actually 4, right? That is for A. That means for B, which is RB, will be 2 to the nth power, which is now 4, right? So we have 16, right? So we have 16. Now let's see. Of course, we know that RA will be N initial, right, over N final, which is N2, right? Of course, this is for A, so it will be for A. So that of B will also be N initial of A over N final of A, right? So let's look at the ratio of RA to RB first. So let's see if that will actually enable us to simplify the problem. So let's look at RA, ratio RA to RB. Now RA will be N will be of course that won't actually work. Let's look at an alternative way. Since we know that RA will be N initial A over N final A, and this is actually 4, right? So since this is 4, that means N2 of A will be N initial of A over 4, right? So same thing to B, N2 of B will be N initial of B over RA. What is RA? Sorry, RB. RB is what? 16. So we have 16, right? So let's clean up some space here. Of course, we are trying to look at the ratio between n2 of A to what? N2 of B, and this will be n2. Where is n2 of A? This is actually n2 of A, so we have n A1 over 4 ratio. Now n2 of B will be n1 of B over 16. n1 of B over 16. So let's look at this here. Right, of course, we said that these two are actually equal, so we can cancel it out, right? So from the equation, it is said to be what? Equal, right? So both of them are equal, so we can cancel it out. So this cancel out with this, so we just have 1 over 4 ratio 1 over 16. So we can just multiply both ratio with what? 16. So 16 into 4 is just 4. Then 16 into 16 is just 1. So the ratio is actually what? 4:1. Okay, so we have 4:1 as the answer to this question. Okay, so the percentage of the original nuclide of a sample of radioactive substance left after 5 half-lives is, so this is actually percentage of the original nuclei, right? Left. Of course, if we know, one thing is that if we know the fraction left, it will make sense, right? Because if we know the fraction left and we multiply the fraction left with 100%, then that will be the answer to this question, right? Okay, now what is the fraction left? Now, since you know that FR is equal to N2 over N1, which is actually 1 over R, right? Okay, and we know that R is equal to what? 2 to the nth power. Now, n in this question is actually 5, right? So we have 5, right? So we have 5, which is 2 to the 5 fifth power, that is 32. So in this case, we now have 1 over 32, right? So the answer to this question will be 1 over 32 times 100%. So we just have 3.125, which is actually approximately 3%. So D is actually correct. Okay. So in this question, we have the time it will take certain radioactive material with half-life 50 days. Half-life 50 days to reduce to 1/32 of the original number is. Now, what is 1 over 32 in this case? Right? Because now they said to reduce to, that means this is the fraction remaining, right? Since it is reducing to this should be the fraction remaining, right? So we have fraction remaining is what? 1 over 32. So we're asked to find the time, which is small t, it takes, right? Small t. Okay. Of course, from here we can find our disintegration ratio R, right? Because FR is equal to 1 over big R, now, which is in this case is 1 over 32. Now from here we see that R is actually 32, right? Okay, R is actually 32. So we have T, which is the half-life, which is now 50, is equal to small t over logarithm base 2 of R. What is R? Right? What is R? R is actually 32. So we have 32 So we have t over logarithm base 2 of, now 32 is actually 2 to the 5th power, right? And using the logarithmic law, we can bring this 5 here. So we have t over 5 log 2 base 2, right? So let's clean up the spaces here. So in this case, we now have capital T, sorry. We now have 50, right? Because capital T is actually 50. Capital T is actually what? 50. So 50 is equal to big T, small t over 5 log 2 base 2. Now log 2 base 2 is actually 1. So we have 50 equal to big T over, now what is this? So we have 5 times log 2 base 2, which is actually the same thing as saying 5 times 1, which is 5, right? So cross multiplying, you have t equal to 50 times 5, and this is actually 250 days, right? So this is actually correct. So this is, I think this should be the last question. Okay, this is actually the last question. Okay, in this, now we are actually having count rate in this case. Now they say the count rate of a radioactive material is 800 counts per minute. If the half-life is 4 days, what would be the count rate in 16 days? Now, irrespective of whether you see count rates or amount of atom, now you could still use the same formula, right? So in this case, count rate, initial count rate is going to be 800 count per minute. So you have to find the final count rate, right? Which we don't know. Now we are given the half-life, which is capital T, to be 4 days, and small t, which is 16 days. 16 days, right? So let's see if we can get the number of half-lives. So since n is equal to small t over big T, this is equal to what's small t? Small t is actually 16 over big T, which is actually 4, and this is actually equal to 4, right? 16 over 4 is actually 4. So, and this will be equal to, since now take note, since we have n, since 2 to the n is actually r. Now if you should take logarithm of both sides base 2, logarithm of both sides base 2, logarithm base 2 of both sides, so we now have n comes down here. So we have n running out of space, n equal to log 2 log r base 2. Okay, so since we have this, so let's see if we can actually plug everything here. So let me clean this up. Okay, so n, which is 4, is equal to log r base 2. Of course, we know that r is actually n1 over n2. Now in this case, n1 is actually 800, right? 800 counts per minute. Then we don't know n2, right? We don't know n2. So if we should raise both sides to the raise 2 to both sides, that means we raise 2 to the 4th power, right? That is using the logarithmic law. So we have 2 to the 4th power. Now in this case, we now have 800 over n2, right? Because if you find the logarithm of both sides base 2, we just have 2 to the 4th power in this side. Then, sorry, not the logarithm of both sides, but 2 raised to the power of both sides. Okay, so this cancels out with this, so we just have 800 over n1 equal to 2 raised to power 4. Okay, so we now 2 raised to power 4 equal to 800 over 2. 2 raised to power 4 equal to 800 over n2, right? So n2 will now be 800 over 2 raised to power 4. So I have 800 over 16, right? And this is actually 50 counts per minute, right? 50 counts per minute. So this is actually correct.